This is a tutorial to develop the inventory system model using a process interaction worldview and the SIMPy library in Python. This problem, as we discussed in lecture, deals with managing a warehouse where you have a certain number of products in inventory. You sell those products to customers for a certain price, let's say $100 a piece. Customers arrive with a certain inter-arrival period, and they have a random amount of demands between 1 and 4 products. The key part of this system model that we're interested in investigating is identifying a good order policy. So order policy is two variables, little s and big S. Little s is the cutoff value at which we place an order for more product, and big S is the target number of product that we want to achieve in inventory. There are certain costs associated with placing orders. We have a delay until those orders are actually delivered of 2 days, and there's a holding cost that we incur on a continuous basis for holding products in inventory. To develop this model, we're going to be using a process-oriented coding style. However, you can also use an object-oriented programming style, which removes some of the need for global variables that we'll see later in this example. So to start off, I'm first going to import the SIMPy library and also import the NumPy library and refer to it as shorthand NP. The two primary activities or processes that we're going to be modeling in this case is the overall run process, which will model the operations of a warehouse overall. And then we're also going to model the second process of placing and waiting for an order to be delivered. As precursor, let's go ahead and set up some of our SIMPy environment first. Let's seed our random number generator to just the value 0 to start with. Create a new SIMPy environment, store it as the variable env, and also run this environment for some temporary period, let's say 5 days, just to help debug some of this development. The first thing we can start by modeling is this overall run process. I'm going to define a process, a generator in Python. Define, let's call this warehouse run. This process will need a couple of arguments. The first argument is it needs to know the SIMPy environment that it'll be using. So I'll pass that in as the argument env. I'm also going to pass in two variables to determine how do you run this warehouse. The first is the order cutoff. This is little s in our problem description. I'm also going to pass in the order target. This is big S in the process in the problem description. So in this warehouse, there's a couple of things that we need to do to kind of initialize the warehouse parameters. This warehouse is going to have an inventory level. So I'm going to create a variable inventory and assign it to initialize the inventory to the target inventory level. I'm also going to create a balance to keep track of how much money we have. So this is kind of the sum of both revenues and minus the costs. The balance we'll say starts at 0, and we'll also define a number the number of products that are on order. So similar to the event scheduling worldview. Now, one of the challenges with using these variables inside of a generator is that they aren't necessarily accessible outside of this particular generator. So specifically, when we start looking at modeling the second process, the order process, we need to update the number of products that are ordered. We need to update the balance. We need to update the inventory levels. So all of these state variables, we have to make them global variables in order to make them modifiable outside of this one specific generator. So this is not generally good programming practice. However, for this simple example, it works fairly well. There's ways to get around this, and specifically if you use an object-oriented coding style, you don't need to use global variables. But just for this example, I'll define that there's going to be 3 global variables: inventory, balance, and num ordered. So any other generators where I use the same line of code, I'll be able to access these same values and modify them. Okay, so we can start sketching out the body of this warehouse run method. This is a relatively complex process. This handles the arrival of customers, so waiting for some inter-arrival duration. It handles the holding costs that are associated with holding inventory. It models the random number of demands that the customers require. It handles the revenue we get from selling those out of our inventory and updates the inventory levels we have and possibly generates new orders. So as a precursor, let's just build some of the process generators that we'll need down the road. Let's define a generate inter-arrival process generator. This one is following the specifications of the problem is an exponentially distributed random variable. So let's return numpy.random.exponential. Again, the exponential generator in NumPy uses a scale parameter instead of a rate parameter. So if we want to have a lambda equals 5 customers per day, we need to pass in here a scale parameter of 1 over 5 as the scale parameter. So that'll give us our inter-arrival periods. Let's also define a generate demand function. This is going to return an integer between 1 and 4. So use the numpy.random.randint. The random integer takes a low and high value. However, the high value is it's exclusive. So if we want there to actually be up to 4 products demanded, we'll need the lower bound to be 1 and the upper bound to be 5 in this particular case. Okay, so those process generators are now defined, so we can get into the body of our warehouse run process. First thing we do is to wait for a duration based on the inter-arrival period. So in this method, well, the first thing we want to do is we'll want an infinite loop. So to repeat a series of activities indefinitely. First thing we want to do is generate an inter-arrival period. So we'll assign this to just a variable inter-arrival. This is generate inter-arrival. Then we want to yield for a certain time duration. So yield for the environment dot timeout for this inter-arrival period. So then after we've waited for this inter-arrival period, then the next thing is to update our current balance based on our inventory level, the holding cost, and the duration that we've just waited. So we need to take our balance and subtract from it our current inventory level, inventory, times the holding cost, which in the problem definition is $2 per product per day, and multiply by the inter-arrival period that we just waited, inter-arrival. So that'll update the balance. Next thing we can do is to generate the demand, the random number of products that this customer wants to purchase. So we'll create a new temporary variable demand, assign it to generate a demand for this customer. Then there's 2 branches that we want to follow. One is if we have enough inventory to satisfy this demand, and the other branch is if we don't have enough inventory to satisfy this demand. So let's check if first the demand is smaller than the inventory. Then we can sell the complete amount, and our balance increases by the revenue we make per product, which is $100, times how many we just sold, demand. And we also need to decrease our inventory by that number that we just sold. So inventory minus equals demand. Now in the other case, if we don't have enough inventory to satisfy the entire demand, what we can do is we can sell out the rest of our inventory, and our balance increases by 100 times however many we have left, 100 times inventory, and we set our inventory down to 0 because we've essentially sold everything that we have. So that handles the customer arrival. We may help to print some messages here. So we can say here we've sold some amount of demands. And in this other case, let's say that we sold out. Um, we sold whatever we had left in an inventory, and now we're out of stock. Right? So let's give this, let's see if this works so far. Well, we haven't added in the orders, so we're eventually going to run out of stock, but that's fine for doing some testing. We have down at the bottom of our script our SIMPy environment. We just have to add to it this warehouse run process. So to the SIMPy environment, we want to add a new process, and it's going to be processing the warehouse run generator. It uses the SIMPy environment. Let's say for an order cutoff that we will place a new order if we fall below 10, 10 stock, 10 in inventory. And let's say we start with 30 and we'd like to try to get back up to 30 inventory. So if we run this for 5 days, we can see a trace of what happens. So it looks like our first customer we sold 2 to, the next purchased 4, then 2, 3, 3, 1, 3, 3, 2, 1, 4. And then at that point, we're out of stock, and all of the additional customers that come in, we can't actually sell them anything. Maybe just to make this a little bit easier to read, I'll also print out the time that each of these happens at. So there we go. At each of the times, it tells us how much we sold. This isn't very nice to look at. I guess with all of the decimals, it's kind of confusing. So I'm just going to rewrite this and put in another curly bracket so I can format the current simulation time to make it look a little bit better. So here inside of these curly brackets, I can pass in a format. So :.2f means we want to format the number in this curly bracket, format as a floating point number with 2 decimal places. So this will just make it look a little bit better as outputs. So indeed, now we're seeing that looks like we've sold out of stock. Just I think we sold out just about on just before day 2. So we'll need those new orders to be considered to replenish the stock in this kind of example simulation. Okay, so the next thing we want to do is to start working on the logic for whether orders should be placed, and then defining this new process to place the order, wait for a period of time, and then replenish the inventory levels. So still working within our main kind of run method, we've gotten to the point of selling to the customer if we can or if we can't. Then we want to make a check if our inventory is less than the order cutoff. And we also need to check to see if we don't currently have an order that has been placed. So num ordered equals 0. So if our inventory is below the cutoff when we haven't placed an order yet, then what we essentially want to do is to place a new order. So there's a couple of ways that we can figure this out. We can either figure out how much to order inside of the warehouse run method, or we can figure out how much to order inside of the order method or inside of the order process. And let's actually do the second. So if this is the case, we're going to launch a new process, and we're going to call it the order process. So let's define this real quick. Define a new process. Let's call it handle order. This needs to know the SIMPy environment that we're going to be dealing with. So in this case, where we need to place a new order, within the SIMPy environment, we'll process a new handle order process and pass in the SIMPy environment. Now, as I mentioned before, this handle order process needs access to some of these global variables. It needs to actually write new values to them, so it needs to explicitly define that it's going to be using the global variables inventory, balance, and num ordered. So I'm going to copy and paste that instruction inside of the process. The first thing to do is to figure out how many do we need to order. So the num ordered is our order target minus the inventory level. However, we can see here this order target has not been defined inside of this process. So we'd either need to make this a global variable or more preferentially pass this in as a second argument to this particular function. So whenever we do the handle order process, we'll also need to know what is the target that we're trying to achieve. So that gets passed in as an argument into this function. So the number ordered is going to be the target level minus the inventory. We need to, so that's the step here in the activity diagram. We need to adjust our balance. So the balance needs to have subtracted from it the cost, which is 50 times the number ordered. We then need to wait for some period of time. We need to wait for 2 days. So we're going to yield the environment.timeout for 2 days. And then after we finished waiting for that period of time, then we can increase the inventory to add in the number that were ordered, and then reset the number that were ordered back to 0. So let's take a look at how this works. Well, just let's add in a couple of print statements. I'm just going to copy these for convenience. So right when we enter the handle order process, let's say that we want to we placed an order for some amount. Put it right here after we figured out how many we need to order. And then after we've waited for the timeout period, the last segment, let's say that we received the order, and we don't need to have any more information. Well, let's have how many we have in inventory now. So blank in inventory, and we'll use the inventory variable to format that string. Okay, so let's run this. Looks like in the simulation, the first customer came again, at time 0.16, sold 2 to them, 4 to the second, 2 to the third, so on and so forth. Looks like we must have had under 10 inventory at this point in time, at time 1.44. We placed an order for 21 new products at that time. So this is when our inventory level dropped below 10. And then we continue selling afterwards, but we don't actually receive our next order until day 3. Until the fourth day of operations at time 3.44. So when we receive this new order, we still only have 21 in inventory. So this is telling us that it may not be the ideal steps or the ideal parameters for this design problem. It gets a little bit tricky to read through these event traces like this, so let's work on adding a couple of visualizations to this. One of the key items that may be of interest is to track the amount of products in inventory over time. So we could put in could create some variables and track this information inside of the other events. But just an easier way, again, is perhaps to use a process monitor. So we can define some new variables like the observation time, create just an empty list, and then the inventory at that time, inventory level. And using these variables, I can create a observation process to observe the simulation environment. And inside of the simulation environment, this will be a continuous process that will always loop around itself. So while true, we want to record our observation time, append the environment.now, and then for the inventory level, we want to append the current inventory. Now in this process, it's probably good practice here to define that we're using the global variable inventory. It actually works even if you don't define this because we aren't modifying this global variable, we're just accessing and reading reading its value. So now if we rerun the simulation, forgot the key part of this, to make this a generator, we need a yield keyword. Let's yield every 1/10 of a day. So this will make observations 10 times per day. If we rerun the simulation, we can take a look at our observation time. Looks like it was, we forgot to add this observe process to the simulation. So just down below, we need to take our SIMP environment, add a new process, the observe process, and it's observing this particular simulation environment. Rerun the simulation, take a look at the observation times. It does look like we're getting observations every tenth of a day. We do see some floating point issues. So it's actually very difficult to represent tenths of numbers precisely in floating point numbers. So, but for visualization, this shouldn't matter. And our inventory level also has data in it, so that looks good. So let's build a visualization of this. I'm going to import the matplotlib.pyplot, refer to it as plt, create a new figure, and let's plot using a step function. The x-axis will be the observation time, y-axis will be the inventory level, and let's use the post option on where to put the straight lines. The x label is the simulation time. This is in days. And the y label is the inventory level. Right? So we can see here that based on this simulation, our inventory level starts at 30, it decreases down to 0, and then it gets replenished when our reorder takes place. This is helpful to then test other strategies. We can, for example, increase our cutoff maybe to 20. This will place an order earlier. So this placed an order right here about at time 1. However, the order that was placed was only for about 10 units. So after the 2 days later, we see that 10 units that gets delivered really isn't enough to satisfy the demands. So for this particular run, it looks like it would be more effective to have a larger initial inventory level and maybe an intermediate level for the cutoff. So for 50 units, this one seems to achieve the goal of not falling below 0. However, there's some challenges. This is just the results for one particular random number stream. If we change the seed, we get different behaviors. So any particular decisions you make for the system would have to be evaluated for a number of random number seeds. The other challenge for this particular problem is we don't actually really care about the inventory level. What we're more careful about is our total balance. So our balance was stored as the balance variable. This particular run recorded a final balance of about $3,300, $3,250. There's a real risk to having too much inventory on hand. The holding costs associated with having this much inventory may actually outweigh the benefits of being able to sell to the last couple of customers. So you need to do a careful analysis across a large number of random number seeds to identify what is the